Ice Cube to Bunsen burner, you melt me. Bunsen burner, it's just a phase you're going through. Welcome to Changes of State. Today we're going to take a look at what happens when we change the state of matter and how all of these interactions actually occur on a molecular level. So grab a writing utensil and let's get going with your notebook. So changes of state, we really have these phase change points that we will be talking about throughout part of the rest of the year. And so we have things like boiling point and melting point and freezing point. And really these are all temperatures at which these phenomena are going to happen. And so if we take a look at water, we notice that water has specific boiling point, melting point, and freezing point. And so if you know a little bit about water, you know that the boiling point is actually 100 degrees Celsius, okay? And that's at 1 atmosphere pressure, so 100 degrees Celsius. And the freezing and melting point actually happen to be the same temperature. It just depends upon the direction that we're going. And those are going to be 0 degrees Celsius. And so what we see is that this is going to boil. So this part right, let me grab a highlighter here. This point right here where we're going to go between the liquid and the vapor is going to be 100 degrees Celsius. And then between water, okay, and ice, we're going to have 0 degrees Celsius. So one of the really big driving forces behind phase changes, and we're gonna take a look at the thermochemistry or the energy exchange of this later on, or the intermolecular forces. And what we find is that those intermolecular forces are a very important factor as we are moving through our phase changes. And so if you remember from before when we studied these, they're the attractive forces between different molecules. And so it's how molecules stick together. The closer those molecules are, the more likely they are to have intermolecular forces. And so we see that there's an amount of energy that we have to overcome to break those intermolecular forces as we change the state of matter. And we'll come back and talk about that a bit more later. But the closer those molecules, the more intermolecular forces. And so we really technically, in most cases, and I'll say in most cases because we'll see some variance from this, but we should normally see that the highest amount of intermolecular forces happen with ice, and we see definitely the lowest amount of intermolecular forces will actually be with gases. And we actually say that these basically will have no intermolecular forces. That's not always entirely true, but we actually make a lot of assumptions with gases that if they behave ideally, they're not going to have intermolecular forces. So that's just kind of a little bit of background information there. So in order to change phases, we have to break these intermolecular forces, or these attractive forces that hold together these different states of matter, or molecules in these states of matter. All right. So let's take a look a little bit further at what happens. And so we're going to start off with our gas and our liquid and our solid. We're going to ignore plasmas for the most part because these are the three that we generally tend to come into contact with in most situations. And so we know that as we work with these, we see that there's an increase in energy and an increase in molecular motion, and these are going to be designated by the red ones. And so between our different ones, we see that between a solid and a liquid, if we're going from a solid to a liquid, we're actually going to be increasing our energy, or our thermal energy, and increasing our molecular motion. So we go from when these guys were vibrating to when they're freely flowing past one another. To go from a liquid to a gas, we have what we call evaporation. Okay? If you remember the water cycle, probably from maybe grade school or at least middle school, we talked a lot about these things at that point. Okay, there's also another one called sublimation. Probably the most common example of that is if you see dry ice. Dry ice is actually frozen carbon dioxide, and it goes straight into gas form if you set it out at room temperature. All right, we're also going to go the other direction, so let's move me here. And this is where we're going to see that there's a decrease in the energy and molecular motion. Okay, and so we can go the other direction. We can oftentimes decrease our temperature or our thermal energy. And we see that if we're going from a gas into a liquid, we see this process is condensation, or we condense that gas down. And once we start to condense it, it starts to form a liquid. Okay, As we're going between a liquid and a solid, we see that there's freezing. Okay, so we've talked about freezing point and how that's that temperature at which that's going to happen. And then deposition. Okay, so deposition is going from a gas to a solid. I don't think that we see as many examples of these two, the sublimation and deposition, but they do actually happen. But we see a lot of these ones between the freezing and melting and the condensation and evaporation. And so we want to know about each one of those things. And really the big deal is that as you are moving, okay, as we're increasing molecular motion, we see that there generally tends to be a decrease in the intermolecular forces, okay, in general. And as we decrease in energy, okay, there tends to be an increase in those intermolecular forces. So I think that's a good thing to keep in mind. Now that's a pretty general statement. There are some substances that sometimes that might deviate a little bit from as if we were to look at it more specifically. Okay. So what we want to do is we want to look at this phase diagram. This is actually a pretty important concept for us in chemistry. And with this, we see some different points that we want to really highlight, okay? And so this, we see that over on this side, there's a pressure amount. Remember, we talked about how we can have increases in pressure that can change the state of matter. And we also have temperature. And so phase and state are going to be kind of synonymous with one another. So we see that there's a solid here and a liquid and a gas, and they all have their certain places where they're going to be. If you were to cross this particular line, let me get a different color here. We'll do a yellow line here. So this line right here is actually representing the line across which melting and freezing point happens. So this is a little bit different diagram. And so as we either increase temperature, okay, we can go from a solid to a liquid, or if we increase pressure, either way, these are the things that are happening along this line here, okay? We can also see down here that sublimation and deposition can occur. So we see there's a line right here. And so this is where you can go directly between a solid and a gas. And so, of course, our temperature doesn't look as high here, but if we have lower pressure, we can see that happen as well. And so that can happen. And it really depends upon what substance we have as to what the temperature and pressures for those substances would be. And then over on this side, we see that you can go between a liquid and a gas. And we see that this is where vaporization and condensation happen. If you notice right here in the very center, we have this thing called triple point. Okay, so triple point, what on earth is this? This is actually the place where we can see all three phases together. And so we can see all phases or states can occur simultaneously, okay, at the same time. There's also a point up here called critical point, and this is above where liquid no longer occurs. So liquid does not occur, okay, no longer, I'll say, no longer. So those are a couple other important points that we see on that. So let's take a look at probably the most famous example of this, which is usually going to be water. So we know some things about water, and so this actually gives you some specifics about temperature, and so we can read one of these to find out a lot of different information. So for example, we see that the normal freezing point, we'll talk about some differences from that, is right here. And if we go down, we see that that is going to be at 0 degrees Celsius. And over here, we see the normal boiling point is at 100 degrees Celsius, okay? And that's if we are also at 1 atmosphere of pressure. So we know that as atmospheric pressure changes, that the boiling point will change. For example, if you go higher up on a mountain, we find that the amount of time it takes to boil or the temperature it takes to boil is a little bit lower, and that's why they tell you to boil for longer to make sure that you actually don't have anything that you don't want to get into your body with microbes that are still going to be living. Okay, we see the critical point is going to be at 217.75 atmospheres, and it's going to be at 373.99 degrees Celsius. And so that's above the point which liquid water no longer occurs. Okay, so if we were to highly pressurize it, it would definitely turn into a vapor. And so we can tell all different sorts of things from here. We can say, okay, at this temperature, what is, and 1 atmosphere, what's water going to be? And whatever this temperature would be, say it was 50 degrees, okay, Celsius, we know that it's going to be a liquid, okay, so we know that that's going to happen. But we could say, hey, if we were to lower it to such and such a pressure or raise it to a pressure, what would we see as well? And so that's kind of a handy thing to be able to look at and just to be able to evaluate. And that data analysis or that graphical analysis is a very important thing. I hope that's helpful for you. And just to leave you with one more thing, the next time somebody says that they're melting, you might be able to explain why. Until next time.